All right, reporter or reporters, your time is now up. If I could get the name of the people presenting.
Liam Bonds.
Okay, cool. Good luck, and you have now 10 minutes to present, and I will let you know when there's a 1-minute warning.
Okay. I'm going to share my screen. Oh, I shared it the wrong way. Oops. Okay. Sorry about that. I hope my time hasn't started yet. Present. Okay. So I'm doing problem number 12, the metallic forest. And so the problem statement is, in the electrolysis of aqueous solutions of metal salts, fractal-like dendrites can begin to grow gradually on electrodes. How can the dendrite shape and fractal dimension be controlled by choice and variation of the setup parameters? And so the actual physical phenomena generally is you have a metal salt, in our case zinc sulfate, and you dissolve it in water, and that disassociates into ions, which in our case would be zinc and sulfate. And, oh, sorry. Jeez. Oh my gosh. Okay. Sorry about that. Okay, we're back. And so if a potential is induced, then you experience a Lorentz force on the ions towards your negative charge. And so since it's in an aqueous solution, the ions are actually going a Brownian motion. And so there's a lot of collisions, and it's not directly towards the center seed. And so once a zinc ion actually hits the cathode in this case, it undergoes a phase transition and aggregates onto the cathode. And as these aggregates build up, there's fjords that form because the probability of avoiding these arms that are built up actually diminishes as they grow. And so our approach is going to be to reduce our system into 2 dimensions to simplify the problem. And then we're going to look for 2 specific parameters to study both qualitatively and quantitatively. So firstly, we're going to do kind of a quick introduction to fractal dimension. Basically, you have measure, and for a line, if you scale that measure, you expect the scale to have a exponent of 1, because that's the dimension it's in. And so if you scale a square by 2, you get 4 times the area, a cube, you get 8 times. And so scaling something is the same as reducing the unit interval by the inverse. And so you see this recurrence of you have your measure is equal to your unit interval to the negative dimension. And so for a fractal, take the Sierpinski triangle. If it's self-similar, it's easy to do this. If you scale this triangle by 2, you see it has 3 copies of itself, and so 3 times its measure. And so we can easily find its dimension, but it's actually non-integer. And so the kind of whole idea is you can have something in a plane that actually acts more like, less like a curve and more like a surface. And so formally, it's a Hausdorff measure and dimension, which is extending the Lebesgue measure into non-integer dimension, but that's not very applicable to real world applications, especially when you're trying to experiment. And so we use the box counting method, which is the same idea of measuring measure versus scale. And so for our system, the first model we looked at to analyze it was a diffusion limited aggregation model. And this model actually is not very good because it doesn't have any bias, and it's only one aggregate at a time. And it undergoes a random walk, and it's Brownian, but it doesn't actually model our situation. And so because of this, it still is accurate at low molarity and voltage, which we will analyze later, but we need to extend it to our situation. And so the theoretical model we're going to follow is Michie-McCohen and Coe's treatment, which induces an electrodynamic force and can also model multiple particles at a time. And so the theoretical model starts out without electric forces, and it's just the diffusion equation, and it's assumed to be in equilibrium, so it becomes a Laplace equation. And this is modeled discretely because it's going to be a numeric model, and in the original paper they used it to do a program. We don't do that here because I don't know how to program. And so there's this large equation. It will simplify later. And so we take equal separential differentials of this known solution to the Laplace equation, and it simplifies into this equation, which is modeling, C here is the concentration, which would be molarity in our case, at a point xi, yi, but it's being measured off of the concentrations of the points around it. And so it's very useful for a numeric model because you can do it recursively. And with that, you can really easily program this and have it create a fractal from aggregation. And concentration equations are actually, in this situation, are actually completely analogous to probability. And so we can also use that as well. And so again, it uses almost a recursive relation to model the probability of it being in position based off of the 4 adjacent positions around it. So, if it's been in one position, it has an equal chance of being in all their 4 positions because we have not yet induced the electromagnetic force yet. And so that's what we do next. So now that we're going to add electric forces, our diffusion equation actually becomes this equation that includes the field. And so it's the time derivative of concentration. And so here, mu is the ion mobility and E is our electric field vector. And again, we assume equilibrium, which is not a very great assumption, but it vastly simplifies our equation. It becomes homogeneous. And so we need to further simplify this if we want to get a numerical situation that we can actually model. And so ideally, because you have the nabla dot E here, which is analogous to your Laplace, or is your Laplace, if we could assume the charge density was 0, that would be ideal. But even small variations in it create really large local field fluctuations. And so we actually assume, as McCain and Coe did, because we're following their derivation, that any field flux or changes is distributed evenly and all points towards the cathode. And so doing that, we can call local field changes to be external field changes. And this allows us to apply Laplace for charge-free space. And so that simplifies this last term here to be 0. And so then we get this differential equation. And this, can be in continuous terms is this. And so we follow McCain and Coe. And so they define a dimensionless units in order to simplify it further. And C naught was the overall molarity, and A is the chosen discrete spacing or the differential. And so we also define more dimensionless units to further simplify the equation. And it becomes this differential equation here, which can be easily solved, or not so easily solved, but they solved it into becoming an equation for concentration as before, but now with an electric force. And so using this, you could numerically model and simulate most of our system's conditions. We don't do that, but we wanted to demonstrate how it would be done. And so from this equation, the concentration can also give us an idea of how our fractal dimension is going to be dependent upon concentration and the electric field or the potential. And so in the original diffusion limited aggregation paper, they correlated the concentration to your scale, which is R here, and the fractal dimension and the dimension of the medium, which is the small d. And so we just basically use this idea just to say, okay, now that we have this complicated numeric model, we can understand how we can get fractal dimension based off of that. And it's going to be somehow related positively to field and concentration. Since this is a diffusion situation, thermodynamics is very important, but because we can't control any of the thermodynamic variables, we forego going through a specific model on it because we wanted to focus on electrodynamics. But we can kind of take an important characteristic off of thermodynamics, which is isotropy and anisotropy, and relate that to our system. And so isotropy is basically the idea that things are the same in any direction you go. And anisotropy is the idea that going in specific directions, you have different characteristics. So like think about a grain of wood, you have going inside the grain, easier to cut than going against the grain, that whole idea. And so what our paper we're referring to here claims is that the transition between these kind of diffusion limited aggregation models and more dendritic models is that there's
Unfortunately,
more.
the time is up.
Really? Wow. Okay.
Yeah, that's fast, isn't it? Thank you so much for presenting.
Okay.
Can I get the name of the opponent?
I will do it.
All right, Shantanu. So now we have 2 minutes for the opponent to ask clarifying questions to the reporter. And once again, I'll let you know when 1 minute is remaining.
Okay.
Go ahead.
So I'll try to keep my questions pretty short. Oh, if you could keep your screen share, would you mind, Liam?
Yeah, no, for sure.
I wanted to look back at 2 of the slides very quickly.
Of course. Screen share. There we go.
Thank you. So the first thing is, could you go to the very first slide and just go down? I think it was maybe 1 or 2. Can you go down 1, please?
Or this one?
Oh,
what was
sorry,
it about?
Next one. It had the word cells on the page. I can't remember where it was. Down, yeah, if you wouldn't mind just going through them, I'll tell you when I see it.
That's okay.
Keep going. It was after the discussion on fractals. Yes, okay.
This one?
Yes, okay. Could you just like very briefly, 1, maybe 2 sentences, explain to me again what is the cell in the context of the problem?
Okay, so our physical, we're going to get to that, but the experimental setup is you have a very thin, so it's almost analogous to 2 dimensions, a layer of water, deionized water mixed with your sulfate. And then you have a cathode poking into the center of it, and then a circular anode surrounding it that creates a uniform field that aggregates your ions onto the center. Does that make sense?
I think that makes sense, yes. Can you continue to go down through the slides, please?
Sure. Did I pass it?
No, keep going.
I kind of went through 3 really fast.
Keep going down, please.
Okay.
Unfortunately, time is up again.
Okay.
Sorry about that. So now the opponent will have 3 minutes to prepare, and I'll once again let you know when 1 minute is remaining. All right, your time is now up, opponent. And so now you have 5 minutes to present.
Okay, I will share my screen. Can you see it?
Yeah.
All right, you can see problem 12 opposition. Is that correct? You can see that?
No.
No.
It's the itinerary right now.
Oh no. Okay. Let me try that again very quickly. Aha, I found it. How's that?
Yeah.
All right, so hello, welcome one and all. Thank you so much for your time. My name is Shantanu Kadam, and I will be speaking on behalf of string beam theorists, aka UC Berkeley, in opposition of problem 12, which was wonderfully presented. So first of all, let's start off with the problem statement, which Liam did an excellent job of reminding us of. In the electrolysis, I'm getting all tongue-tied. I'm going to skip the word. In the blank of aqueous solutions of metal salt, fractal-like dendrites can begin to grow gradually on the electrodes. Here are the key words. How can the dendrite shape and fractal dimension be controlled by choice and variation of the setup parameters? So please keep those things in mind as we go through the how, as well as choice and variation in relation to those two parameters, or in relation to those two characteristics, dendrite shape and fractal dimension, will play a really big role in how we can develop this solution together, I feel. So first of all, let's start off with the positives. The theory was really well done. I was amazed and really delighted to see that there was previous literature on the topic and that these researchers took it upon themselves, and Liam and everyone else who worked on it took it upon themselves to go out there and see what was already done. And the consequence of that, I think, and a testament to their thought process, is that there are very clear assumptions from the beginning. When assumptions were being made to simplify the process or to understand the phenomena, it was abundantly clear and generally very reasonable. Additionally, there was a very coherent physical basis from Brownian motion and also Laplace's equations, which was very interesting and very exciting. I think that speaks to a very successful simplification of what appears to be a complex problem. And there was definitely a very solid foundation in mathematics, and I appreciated the introduction of fractals. It was very exciting to see this diffusion limited aggregation model, and the use of not just one, but two models and explaining the nuances, again, shows that mathematical foundation. There is unfortunately not anything positive to say about the experiment because there was either not enough time or there was no experiment. I'm unclear, and I'm hoping we can discuss that in the next in the next phase of this event. And last but certainly not least, presentation. As I've already said, there was a very clear and firm grasp of mathematics and theory, and the flow of ideas was very well motivated. And it's just unfortunate that the time management wasn't, or there was just perhaps a lot of material. So let's move on to some of the things that we think can be discussed, and moving forward, we can together hopefully, or maybe we can just hear your thoughts on what can be done to make the solution even better than it already is. We did find that the chemistry introduction was a little unclear, and perhaps having some sort of visuals, pictures, which kind of goes down to presentation at the bottom of the page. Having some visuals may have been of assistance in some manner. Having said that, we do acknowledge that it was a research paper that was probably very complicated. So definitely having visuals could break it up and make it easier to digest and understand what's going on. And a lot of the prereqs were explained well, but sometimes there were some foreign terms or perhaps terms of the field, especially in the first 4 or 5 pages with the chemistry, that may not have been clear. So it'd be nice to perhaps revisit those. Specifically the second DLA model, you had mentioned it, but it wasn't obvious what exactly the model itself was, I guess what it was predicting or what factors went into it. And I think this was one of the biggest things, and you'll see this again in a few minutes, but there was no verification of the theory via code, simulation, or experiment. And this is a huge bummer. And so I think one positive is that you drew from a great and really well-developed paper or set of papers, and that is a good thing. But on the other side, it is also a little bit of an unfortunate thing because it was that kind of like leads to this concern that perhaps because it's all theoretical development, if we were to go and try to do an experiment based off of it, we don't know necessarily whether it would or wouldn't work. So that kind of ties into the experimental aspect. The last thing I will say about theory that was concerning to me and that I'd like to hear more about from you all is identifying the key parameters or the choice parameters. And that's the biggest topic I'd like to discuss. Moving into the experiment, obviously the lack of experiment is really concerning, namely because it doesn't verify the theory, but also because that's half the prompt, or most of the prompt, really 80%, because there's this question of how to control the dimension and variation. Yeah. And I will move on now to two last things, possible improvements, and then questions I'd like to discuss with you during our discussion time and beyond that in terms of making the solution even better. First, for possible improvements, it would be exciting, and maybe you have considered this, but we would maybe suggest considering the reservoir, the medium in which the electrolysis is taking place, changing that maybe.
All right, the opponent, your time is now up.
Okay.
Sorry about that. All right, so now we're going to go into discussion between Shantanu, the opponent, and the reporter, Liam, for 5 minutes. And after the 5 minutes are up, anybody from the team members can ask questions or comments.
I guess, Liam, these were the questions specifically, and just like you, I committed a bit of a time management difficulty, but these are the questions specifically that we were wondering and we'd like to hear more about.
May I show you the experiment? I'm not sure if that's in that list.
Come again?
May I show you the experiment?
Yes, I think that'll help answer quite a few of these questions. Shall I stop sharing?
Yeah. Thank you. Okay.
I think we have 5 minutes, so.
Yeah, I won't take up the whole 5 minutes. So just a really quick, just to introduce, here are some morphologies. They're going to come up soon. Sparse dendritic, dense radial, and diffusion limited aggregation. And so our first parameter was concentration, because it's something we could easily control. And as we showed before, it was very, very potent in the theory. And also the voltage, because there's another thing we could control. And so this was our experimental setup. And I can show you the cell. I'm not going to really go through it too much. If it spends too much time loading, I'm just going to skip it.
Okay. Is this a setup that you did at your that you guys actually did?
Yeah, I did this last night.
Okay.
Yeah, and so basically I took a Petri dish. I ordered a lot of Petri dishes. I screwed a very small hole into the center that I could fit pencil lead into. That was my cathode. And then I had this copper wire that goes around the outside that it's touching the liquid. And then I also had two giant clippers hold it down. So it was very thin, less than a millimeter actually. And so that was the general setup, and it's like a time lapse, so you can see it grow.
And so you were controlling for the two parameters that you mentioned above?
Yeah. And so we actually constructed a phase diagram based off of this. And so we showed with variation of concentration and voltage, we could produce a different phases. We produced sparse dendritic with concentration over 1 molar.
Liam, to be honest, this is interesting, but I want to get through some of the other discussion questions as well, and then maybe come back to this one if you don't mind. Because I guess you've answered what the key parameters were that you chose, and I'm wondering, based on the theory, what did you expect for the key parameters?
Oh, yeah.
When you varied them, what did you expect to see in the experiment? Is that what you ended up seeing?
This was from the paper that the theory came from, and this was their phase diagram. And if you see, you can directly correlate the, actually, I will say, their units were wrong, which threw me off for a long time. This was in the physical something.
Wait, so just to clarify, so
yeah.
That's their phase diagram, and the one above is your phase diagram?
Yes, this is the one I did.
And is it in agreement? It's not clear to me.
Yeah, we can look through that right now. So if we start out with dense radial,
right,
like that, it's between it's over 10 voltage-ish, and then concentration over 0.01, but lower than 0.1. And so if you look at mine, 0.1 below, over 10.
So were there any that didn't align with
The one part I was confused about was these two down here, because they seem like a mixture of the dense radial and the diffusion limited, because you can see they kind of look like these really dense towards the center, and then out towards the edges, they get very branchy. And that was not in this phase diagram, so I was kind of confused by that.
I see.
But otherwise,
could you just clarify for me, like when you, so your key parameters, if you increase each of those, how does that affect the dimensions and the fractals, or sorry, the dimensions and the other?
Okay, so from the original DLA paper, your concentration is close to equal to it's what's the word?
So like if I increase concentration, does that
increase? It increases. It should increase the dimension, and increasing the dimension, if you think about it, that is increasing the measure. It's increasing how complex, how much space it fills.
What about the dendrite shape specifically?
Well, the dendrite, it's such a complicated system. There's not the theory, like no theory exactly, explains the shape exactly. But if you think about the measure, you can see how.
And now, sorry to interrupt really quick. All team members can now participate in the conversation.
Okay, so you're saying that as you increase, so you couldn't really explain dendrite shape, but by controlling concentration and what was the other parameter? Voltage, I think?
Well, I can't explain it, but I can produce it, and I predicted, actually, if I had been able to get there, I predicted exactly from the previous paper, because that's what I based it off of. I predicted what would change when changing these parameters, which you find here.
Okay, and just to briefly clarify, the DLA, these are all the different models, is that correct?
The DLA is a model, but it's also just a type of growth. These are different morphologies, so they're different shapes.
Did you visually inspect them to determine which growth was which?
Yeah, if you look at it's like a well-known thing in the field, and so if you just want to look at some of these, and then kind of compare them to mine, you can
So
see
it actually sounds like, now that we've heard about the experiment, there's a lot of like really great progress y'all made, and like taking the paper and like really using it in a great way. So what I'm kind of wondering now is, the problem is about like controlling these parameters to influence these characteristics. How would you optimize control of the dimension of the fractals?
So that is actually a really interesting part. So the we were optimized. What do you mean by optimize?
I guess, well, I mean, you've done the experiment, right? So like if you were to if you wanted to produce a result consistently every time.
So the reason I can't answer that is because our fractal dimension data did not work. We had an algorithm that had a very close approximation to many fractal forms, but then when we actually tried to apply it to our images.
So this is a whole new world. I didn't. So what is this code simulation? Is that what's happening in these last few? Because I see some errors over here, and I'd like to know what those are. But one thing we were really concerned about was like, it would be really great to have some sort of simulation or code, because like Laplacians and solving Laplacians is a really common thing, right? And even the method you described with the boundaries, that's like definitely something that like I think I have a book about coding somewhere here where like I learned how to do that.
Like if I was given another 8 months, I could have learned how to program that, but I didn't. I didn't do a numerical simulation, but
I'm sorry, I don't mean to bash on you. I'm just saying like I definitely see that as like an easy way to like improve on this, because
no, I completely agree. I wish I could have done that.
So what is this code?
So this is the algorithm for taking an image and then calculating fractal dimension, and it was working perfectly up until last night when I had all of my data and I was trying to calculate fractal dimension, and nothing came out. But so these were some of the images we produced of the fractals I made. And so
you took those photos?
Yeah.
In the Petri dish?
Yep.
I see. Wow, that's really amazing. So I guess one thing is, so like looking at these kind of structures, did you notice that different like salts or different electrolytes produce different patterns?
So we only focused on one electrolyte because we wanted to only do two parameters, being the molarity and the voltage. But I would assume that it would depend on the ionic what's the word? the ionic level. I don't really remember. I haven't done chemistry in a while, but like, you know, zinc is +2.
Right.
So I would assume that would affect it.
Right. And I have an inclination to agree with you on that statement. I guess so obviously you determined 2 setup parameters, and now it sounds like you've kind of explored it. And unfortunately, the program just like stopped working.
Yeah.
Otherwise, so if the program had been working, you would have been able to compare the analysis of these images with the dimensions you would predict from the model. Is that?
Yeah, I would crop them, obviously, so the water droplets weren't there. And then I would try to get a comparison of, you know, how does fractal dimension change with change in voltage and change in concentration.
I see. And were there any difficulties in this setup? Like anything that if you were to continue investigating this problem, you would try to do differently? Obviously,
it was really hard. It did not work until last night. If I could change one thing, I would figure out how to get rid of these bubbles. I don't know how to.
Are these bubbles on the Petri dish themselves?
It's inside of the Petri dish. I think it's somehow when the it's when the zinc goes through its phase transition, these bubbles, like, I guess you could say.
Unfortunately, the time is up.
Thank you for your question.
So now the reporter, Liam, you have 1 minute to summarize.
Okay. So I think we succeeded in kind of reproducing a very delicate and very beautiful natural phenomena that was very hard to produce. And we did show a correlation between, you know, our setup parameters that we chose and the different phases. And we compared that to a previous paper, and it was pretty accurate. But otherwise, we did fail on the entire front of doing the fractal dimension. And had we managed our time better and done it before, that probably would not have been an issue. But you know, we're college students. So otherwise, I think if I were to have more time on it, I would certainly try and introduce a numerical model, and then do the same kind of comparison with the phases and with the dimensions, and try and compare that to my real life data to see if
Thank you, Liam.
Okay.
Our time is up again. So now the jury has 6 minutes to ask whatever questions they may want to ask.